So that's me, and I'll be talking about Neural Sparse Search, starting with some of the fundamentals, followed by a demo, and some differences between sparse vectors and dense vectors, hopefully some benchmarks and some best practices that I learned along the way, implementing it for some of our customers. Yeah. For the fundamentals, so this is what I would say, right? So there is this problem called the vocabulary mismatch problem. You think you do not know about it, but you have already experienced it. And the problem goes like this, right? So you want to buy a sofa, and you go on an online website, you search for sofa, the seller is selling sofa, but they have, in a different name, they call it a sofa bed, or they call it love seat, or divan, or in different names, yeah, or couch. And that's a very good example, right? So you're not able to find it. Even though they sell what you're looking for, you're not able to find it, and also not able to buy it because you're not able to find it, right? So this is the vocabulary mismatch problem. And there are several ways people have solved this problem in the past. One classic way is that if you go to some of the shady websites, you can see in the product title, they say sofa / divan / couch / something something / something something. And this is to, regardless of what you search for, they want you to find the product, right? And they called it search engine optimization. This is what they called it, and this is how they solved the problem. But then, I mean, if you actually have a search engineer in the team, the actual nicer way, or the legit way, if I should say, is by having some kind of synonym dictionary or a lemmatization dictionary, and you put it in your search engine, and when a document is being indexed and the products are being indexed, based on these dictionaries, the terms are expanded. Yeah. And these dictionaries can also be used at search time, both ingestion and search time. Yeah. But the problem with this approach has always been curating these dictionaries. So if you're in a public-facing domain, right, you can download some of the open source dictionaries, probably works just fine for you. But let's say if you're in pharmaceutical healthcare, or you're in oil and gas, right, or automobile, any of these dictionaries that you might download may not make super sense for you, yeah, because these. So then someone has to manually curate these dictionaries, and that also means it's exhaustive. Also means it is never comprehensive. You cannot complete the dictionary, putting together the dictionary, right? So this is a long-standing problem. There are also tools such as Quirky and things like that that people use for synonyms. But then came splade. Splade is a type of model. Splade is a sparse lexical and expansion. Came out in the mid of 2021. And what it does is solves this particular problem. So what it does is it does learnable term expansion. So basically what that means is it expands the terms just like how the synonyms does, right? But then it is also contextual driven, so which also means, let's say you have different products or different documents about Apple. One of the document is talking about Apple as a device, the other talking about Apple as a fruit, right? So if you try to put a synonym dictionary file, it's a static synonym file. So Apple can be expanded into just few words in a static way, regardless of what Apple stands for in the overall context, right? What splade does is it does learnable term expansions, which also means that it expands the term based on the context, yeah? So this is a very good example that I show to my customers. So you have two documents, Apple products are expensive, and Apple array keeps the doctor away. And what you see at the bottom is actually the expanded terms, yeah? And as you see here, right, on the first example, the expanded terms are about the device itself, expensive, chip, money, budget, manufacturer, and things like that. On the other side, you have doctor, daily, medical. So you get the idea. It's entirely context-driven. And the even more nicer thing about it is it's not just the term expansion, it also is about the weight. So you also are given a weight of the expanded terms. So because not every expansion is the same, yeah. So then you use the weight to determine how relevant is the expansion for the given terms, yeah. So this is basically the sparse encoding, yeah. And this is document time. So when the documents are ingested, terms are expanded based on the context. And when a search query comes in, you also have to do the same, right? Because, I mean, if Apple headphones, someone is searching for it, they're not really looking for the fruit. They are looking for the device, yeah? So which also means you do a very similar term expansion using the splade kind of model. I'm saying splade kind of model because the model that we will be showing is following a very similar approach, but at the end of the day, it's just term expansions, yeah? So now that you see how the query is also expanded, right? Also with the weights. At the end is about scoring, right? And the scoring is basically a dot product of both the expanded terms from the document and the query and the sum of it. So it's basically a sum of the dot products of the matched terms and their weights, yeah? I will show this in the demo, much easier to understand if you haven't followed how the scoring works in here, yeah? But before that, I will also tell you how you can readily start using it, and that's by using any of the pre-trained OpenSearch models, yeah? So we have a lot of pre-trained models. There are also different generations of model. What I have on the screen is the recommended one, and this is a bi-encoder model, a V2 distill. A bi-encoder basically means the terms are expanded both at ingest time and the search time, yeah? But the problem with this approach is that when you expand the terms during search time, you are doing online inferencing, which will affect your search latency, yeah? So you do not want to do that. You only want to do it doc time, ingestion time, and for that, we have a doc-only encoder model, which is the V3 GTE, the latest generation of the pre-trained models, yeah? All of it is there in Hugging Face. You can take a look at it, yeah? And when you use a doc-only encoder, you also, for the search time, you have to use a tokenizer. For that, we have a sparse tokenizer, and you can also use the starting version 3x. You can also start using the deep learning model analyzer or a custom tokenizer if you want to tokenize your search queries in a different way, yeah? So I will switch screen for the demo. Yeah, and right, come on. Yeah, are you able to see, Dotan? Are you able to see the things expand? Yeah, expand? No. What is it? Oh, wait. This is what I wanted to avoid, but it is happening. Anyway, there is my, oh yeah, okay. So, so this is what I wanted to show. So basically what we will be doing in this demo is deploy a doc-only encoder and test the inference and ingest some documents, and we expect the ingested documents to have the learnable term expansions happening, yeah? And then we will deploy a tokenizer, and then we will run the Neural Sparse Search, which is what, I mean, the whole talk is about, right? And then we will compare search relevancy between the lexical search meaning the keyword-based search that we are all used to up until now, right? And we will compare that with the Neural Sparse Search, followed by two other techniques to improve the search latency if we have time to get to that, yeah? So as a first step, what I'm doing here is I'm allowing OpenSearch to run the model on the data nodes, right? But once again, the recommendation is always deploy your model on a dedicated machine learning node in OpenSearch, or better yet, deploy it elsewhere. Let's say things like Amazon SageMaker or Amazon Bedrock, or if you're on a different cloud provider on the respective hosting platforms, yeah? So that way you are able to, do remote inference, yeah? And for the model itself, what I do is I go to the documentation page, and then I search for pre-trained. If I search for pre-trained, I will land on this page, and I go to the sparse encoding model section. And as you see here, right, these are the recommendations that we were referring to earlier. And now that we have decided, we use the doc-only this encoder, so we find the model in here in the documentation page, and we go to the config URL. Yeah. If you go to the config URL, you will find the whole definition in here. Yeah. So we simply copy it. Yeah. And we simply copy it and we put it here, and that is how we get the model definition. So you find the model and you deploy it. I have already deployed it, and once you deploy it, you will get a task ID, and once you get the task ID, you can check the status of the task ID. Yeah, as you see here, right, because the model is already deployed, line number 5 says it's completed, so which means that my model is already deployed. Yeah. So what you can then do is go to the machine learning tab. Go to the machine learning tab to see the model that you have already deployed. Yeah. So for that, I have already opened the page. Yeah. And I have 2 models already deployed. One is the doc-only model that I showed, right, which is this, and it also tells you on what node it has deployed to. I also get the model ID, which is very important for us to refer when we do inferencing. Yeah. So I copy the model ID, and the other model is basically the tokenizer model that I have. Yeah. So now we go back to our DevTools, right? And this is the model ID that I have copied, which I already have it in here. So when I run the inference, now I can see the expanded terms. Yeah. So you can test. So before even you start doing a full-blown implementation, if you want to check if the model is able to predict the terms in an at least decent way, right, in an appropriate way, you can test it. That's the whole point of it. Yeah. So once that you have done inference, you are happy with it, you want to proceed with it, right? Then the next thing is we ingest the document. When we ingest the document, we use the bulk API, right? That's the regular thing that we do. In this case, what we will do is we will add an interim thing called ingest pipeline. And as the name suggests, a pipeline is a set of processes. In this case, we will have only one processor. So this is a pipeline made of one processor. And the processor is the sparse encoding processor. And the key here is it takes 3 things. One is the model ID, so it knows what model to refer to, and then what field in the document it has to look for. So what field in your doc set has the text that needs to be expanded. Yeah. And once the expansion happens, where should the expanded items go? So which is the other one. So basically 3 things is what bare minimum you would need in your ingest pipeline. Yeah. And once you have it, the next thing that you do is create the index. So in my index, quite simple, I have a text field, which is basically the text field that needs to be, for which I need the sparse vectors to be generated. And the generated sparse vectors need to be held somewhere. This is the field of type rank features. And rank features is a field type that allows you to boost or block the scoring of a sparse vector document. Yeah. And I also set a default pipeline, the pipeline that we just created. Yeah. So that you don't have to, during ingest time, mention what pipeline you want to use. So set it as default, especially if this is the only pipeline that you have. Yeah. I am using Amazon PQA public data as a test data. I have, of course, already indexed it. Yeah, so it's as simple as downloading the JSON file, using the curl command, API, bulk, and yeah, you should have your documents indexed. Yeah. So now that we have the document indexed, we should be able to see both the document and the sparse vectors, which is exactly what we see here. This is the text, and these are the sparse vectors that are expanded to. And this is once again the text and the sparse vectors, and you get the idea, right? So now that we have deployed the doc-only encoder, we have created the pipeline, the ingest pipeline. We have indexed some documents. The expansions have happened. Now we are ready to do neural sparse search, yeah? And for this, we need what? The tokenizer, right? So the tokenizer is, once again, a model that you will find in the documentation page. It's right there, right? Once again, you go to the config URL, copy the configuration, go back, and you will have it deployed. And you can, once again, test the inference, yeah? I'm going a bit faster because I'm running out of time, but basically, I mean, this is how the text is being tokenized. And it also has the weights, as you see here, right? So the next thing that we do is naturally the one that we all are waiting for, at least I am waiting for, is to run the neural sparse search. And for this, we use the search endpoint as always, right? But in here, the query clause in the DSL that we will use is the neural sparse query clause, which takes what field it should look for. So you need to say what field contains the sparse vectors, right? And then you also have to mention what model ID. This is the model ID of the search inference, the tokenizer, yeah? And then lastly, the search text that you want to provide. What are you searching for, right? So in this case, I'm searching for, and this data set that I have is about some question answers about the products, yeah? So this, it's like a frequently asked question kind of data set, yeah? So I'm asking a question like, can I use it as an internet phone, yeah? And as you see here, right, I get the answers. So basically, we are doing neural sparse search. But for us to understand how the scoring works, right, so what you can do is you can explain, set the explain, so it explains the scoring for you, right? So now that we have the first document, it also provides an explanation, all right? So basically what it says is a linear function for the question sparse for the phone feature. So the phone is the text that has been matched. If you look at it, right, phone is here, that's a match. What else is a match? I know for sure the next one is, I believe, use, no? Yeah, use is a match. Use is here, use is also here, so that's a match, yeah? So now if you go look at it, this is the token weight at the doc time, at the query time. So if you look at the inference, phone is 4.58, and we can also look for use is 2.72. Remember the numbers, 4.5 and 2.7, right? So now we go back here, and we see for the phone feature, for the query expansion is 4.5. For the doc expansion, it is 0.7, as you see here. And it's at this point just a dot product of these two, right? Which is basically 3.2. And the same thing happens for the other match, which is for the match for the token use. We once again have the dot product. And once again, this is a sum of the dot products. So you sum 3.2 plus 1 point whatever it is, 1.4, which is how you end up with the, the score. So this is how scoring is done in neural sparse search, yeah. Quite easy to interpret what is really happening inside, yeah. Which is also one of the pros of neural sparse search. Unlike the dense vectors, which is a numerical representation, right? Here, it is very interpretable. You are able to understand what really is going on behind the scenes, yeah. So at this point, we have both the lexical search is already possible because, this is classic OpenSearch BM25, right? So at this point, we can compare the search results because we need to know if the neural sparse search that we are doing is of any value. Right? In order to appreciate neural sparse search, you have to compare it with something else. In this case, we compare it with the lexical search. Yeah. So for that, we usually use the search relevancy tab. Yeah. So the search relevancy tab allows you to compare different search results, which is what I have it on my screen here, right? So this is the search relevancy tab. And what we do here is pretty straightforward, right? So on the left, I have the lexical search, as you see here, right? It's just a lexical search on the field query text. On the right, I have the sparse, line number 4, neural sparse. I'm also saying what model ID, and I'm also saying the sparse vector field, yeah. And we have the placeholder here so that we can pass the actual query to both of these things and to compare them at the same time, yeah. So I'm asking for if there is something in the inventory anymore. So basically I need to know if the product is still available in the market or is it out of stock, yeah. So I run the search, yeah, right? And when I run the search, the first, on the lexical side, the first document is about adapter for system. The second document is about some resolution per eye. The third document is about, I can't read much, price, high. So none of it is about inventory. None of it is about if the product is available or not, right? Which is what you usually get in lexical search, classic keyword match. But then if you go to the sparse search, you can already see all the items in stock. If you look at the actual query, none of the query term had anything about the word stock in it. And this is a very good example of how the Neural Sparse Search can simply get the context from the query and give you relevant results, yeah. The second result is about, straightforward, right? Are they in stock? Is the logistics updated in time, yeah. So this is just a curated example. Of course, there are cases where Neural Sparse Search will fail. For example, if you want to run exact match, like the double quotes exact match that we all are used to, right? The Neural Sparse Search may not work well there, right? So what you will do there, you do lexical search. But then this is why we have the hybrid search, so you get the best out of both worlds. So you are able to capitalize on what lexical search is good at, and also what the neural search is good at, and then combine the results, which is what basically the hybrid search is, yeah. So I will go back, and I have only 8 minutes, so let's see what else we can see, yeah. So I spoke about two techniques that can help you speed up the search, right? Both involve what is called as pruning, yeah. So pruning is basically discarding some amount of data. And how would you discard some amount of data? You probably will determine that certain expansions are not super relevant, and you want to, remove them, yeah. And why do you want to remove them? Or maybe let's look at an example. It's easier to understand if I can find it in time. Oh, it's right here. I'm sorry. Okay, so you look at how there's a long tail of expansions that have happened, and some of them are as low as 0.2, right? So pruning, basically what it does is it discards those lower weight expansions, so you only retain the cream of your expansions, right? What it does is reduce your storage. The less tokens you store, the less is your storage. The less is your storage, the linear is your index. The linear your index, the faster is your search. So that's the whole point of pruning, yeah. And there are quite a few ways to prune. For example, one of the techniques is absolute value, and as it is very self-explanatory. I'm giving a value 0.48, so which basically means any tokens that are weight below 0.48 needs to be discarded. Yeah, there are also prune types such as max ratio that goes in percentage, top 40 percentage, top 40 percentage from the largest weight that you have. Yeah. So this is, once again, the pruning is applied at the ingest time. Yeah, so you discard a lot of elements that you think are not needed. And the other one is at the search time. Yeah, the pruning happens at the search time as a two-phase processor. And this also uses prune line 280, right? So basically, how this thing works is when you run a search, right? What it does is it takes the first 40% of the tokens and run the search and determine a subset of your search, right? And this subset is what will be used for the entire re-ranking. And for when the entire re-ranking happens, it will consider all the weights, regardless of the prune. It will consider all the tokens with regardless of the weight to do the scoring. Yeah. So it improves your search SLA or search latency by quite a bit. Yeah. So yeah. So that's the demo. I have a lot of demo, but I don't have time. Yeah. So let's go back. The APIs that I have and the ones that I do not show also are there in the QR code. And of course, I will upload the deck for a later point in time. If you want to run the demo, you can. Yeah. So this yeah. So there are also easier ways to run neural sparse search in the later models, later versions. It is as simple as this right now, where in the latest version we have this field type called semantic, and the field type takes both the ingest model, the doc-only model, and the tokenizer model, right? So this is during index creation time. You say what field, what are the models, and then you simply index it, and then you start running the search. Yeah, it is as simple as 3 steps, instead of going through the lot of things that I just showed. Yeah, so keep an eye on what is happening in the newer versions of OpenSearch. Things are moving fast. Yeah. This is another justification for why dense vectors are expensive and why sparse vectors are known as budget-friendly. So, for example, if you want to run KNN search for dense vectors, right? With the fires, the HNSW with full precision, right? For 5 million vectors, you already need 16 gig of memory. And you need a 64 gig of memory instance type in order to simply run this 5 million vectors. So what this means is you will run into cost problems sooner or later when you have more and more vectors. If you're doing for 10 million vectors, for example, or 50 billion, yeah, or 10 billion, things would get expensive real fast. Yeah. And for this, you have to have a vertically sized node, which once again is cost thing, right? So why sparse vectors are known as budget friendly is because the data structure that we just saw, right, is ingrained within the native Lucene index. Yeah, it's not a separate KNN index. It's native Lucene index. And because of this fact also, the index size is much smaller compared to dense vectors. And because of the index size being much smaller, the amount of memory you need, the amount of CPU you need is also going down. And that's why it is called, or at least that's why it's known as the budget-friendly semantic search approach. Yeah. It's also good at zero shot, which also means if you're introducing sparse vectors to a newer domain, it's much more, it's probably going to perform much better than introducing a dense vector model to a domain that it does not understand. Yeah. And also when it comes to fine-tuning the model, it's much more not too extensive compared to the dense vector fine-tuning. Yeah. I will not go through the benchmarks for obvious reasons, but I will talk about, in the last minute, talk about the best practices, right? As a summary, if I may, yeah. So use doc-only encoder, much more efficient, yeah. And with the doc-only encoder, you can also use from the latest versions the deep learning tokenizer, which also means you don't necessarily have to deploy a tokenizer, yeah. And always host your models in a dedicated machine learning node in OpenSearch, or better yet, host it elsewhere and do remote inference, yeah. And for the pre-trained models, as of today, we have these models, but tomorrow it might be different, yeah. So which also means anytime you start implementing it, go take a look at the documentation and find out what is the latest, yeah. Sparse vectors right now are efficient until 10 million documents, beyond which we recommend going for dense vectors. But the the way things are moving faster is that last week when I was preparing for this deck, 3.3 was released, and which is when I learned that we have ANN support for sparse vectors, which also means we are able to now scale to 100 million vectors, sparse vectors. So which means this 10 million scaling is not a problem anymore if you're using the newer versions of OpenSearch. Yeah. We saw the Neural Sparse two-phase processor for improving search speed, prune the search vector for compacting, if that is even an English word, for reducing your index size. Keep up with the Lucene version, because just keeping up with the Lucene versions often provide better performance, yeah, thereby reducing cost also for you, yeah. GPU acceleration if you want to speed up the inference, yeah. And also, regardless of what you do, always also adopt OpenSearch best practices. That will take you a long way, yeah. Because sometimes it's not the problem with Neural Sparse Search. Sometimes it's not a problem with dense vectors. Sometimes it's not a problem with something else. Sometimes the problem is you have not followed the best practices, yeah. So always, yeah, regardless of what you do, yeah. And also couple these features with the rest of the OpenSearch features, such as, I don't know, let's say concurrent segment merge or segment replications and things like that, yeah. So this is the feature that I was referring to, new features, yeah. It claims to, I say it claims because I have not tested it myself, yeah, but I believe there's already some benchmarks, and in OpenSearchCon Japan, which is happening next month, the folks who are creating this are speaking about it, so they probably will talk about this, yeah. So the takeaway, use Neural Sparse Search, that's the takeaway, yeah. So a bunch of further reads. I put this in such an order that if you really want to try it, you go through this order, you will be in a good position to understand, you know, what's the linear or, you know, a proper way to understand how to start using it, yeah. And that's my time, yeah. Thank you. Thank you.